Hello, everyone. I just want to pick up where we left off last time, which is that S1 does not map L1 into L1. And as I mentioned, a variation of the example, a very slight variation of the example I will do, which I will leave for you to try and cook up if you're so interested, actually shows that SR, FR, for any R is not L1, and hence this question we asked doesn't even make sense. It doesn't even make sense to ask whether or not this thing converges to F and L1 for all L1 functions, where remember that by definition, this whole thing here is SR. Well, in general, this is SR, this operator. Here, we're applying it to FR. Okay. So if this is not L1 for any R, then there's no way we have convergence in L1 to F if F is an L1. Okay, and you don't have to really search far and wide for such examples. So this is going to be a bit nitty-gritty, but it's not too bad. So let's just look at this characteristic function. Let's look at dimension 1. You can do similar examples in higher dimensions. But yeah, let's look at this characteristic function from -1/12 to 1/12. And I'll mention what's special about 1/12 in a little bit. So we can just concretely figure out what S1 of F is. This is certainly an L1, so we know that this is just convolution with this Dirichlet kernel with R equals 1. So it just cuts off -1/12 to 1/12, sine 2 pi x minus y over pi x minus y. Do a change of variables, u is x minus y, we get the following integral. So what I want to do is very similar to what we did for Fourier series. We want to basically look at certain x and see where the numerator is bounded above. Okay, so let's do that. So let's look at u minus k plus 1/4, for k is a positive integer. Let's look at that absolute value is less than 1/6. This is obviously true if and only if u is in this interval here, k plus 1/4 minus 1/6, k plus 1/4 plus 1/6. So obviously this is just k. Let's see, 3/12 minus 2/12 it's k plus 1/12, k plus 5/12. 2/12 plus 3/12. Or sorry, 3/12 plus 2/12 is 5/12. So multiply everything by 2 pi. 2 pi u is going to be in this interval here. And that's very important. By just looking at the unit circle, basically we're between pi/6 and 5 pi/6, so sine is bigger or equal to 1/2. So we got to figure out x where sine 2 pi u is bigger or equal to 1/2 if u is between x minus 1/12 and x plus 1/12. Well, this is not particularly hard. As long as both of these are true, just use triangle inequality, and we get u minus k plus 1/4, and absolute value is less than 1/6. Okay. Well, what is this here? Well, this is fairly trivially. So I always like to think in terms of absolute values and then translate to inequalities. I think that's just or translated to balls, same thing. That to me is just the easiest way to do these kind of things, but it's up to you how you do them. Right, so this means x is in k plus 1/4 minus 1/12, k plus 1/4 plus 1/12. And so this is just going to be 1/6. This is going to be 1/3. 3/12 plus 1/12, 4/12 is 1/3. Right, so as long as x is in k plus 1/6, k plus 1/3, and u is in x minus 1/12, x plus 1/12, which we said is equivalent to this here. So if both are true, then sine 2 pi u is bigger or equal to 1/2. Well, if x is in this interval, then this is automatically true because u is in this interval here. So this is why we picked 1/12, so that this gives us a nice lower bound for sine 2 pi u. Okay, also, these intervals here are disjoint. As long as k is a positive integer, these intervals here you can check are disjoint. So the L1 norm of S1F is bigger or equal to sum up over all these integrals. Right. So and this is sine 2 pi u. So this here is bigger or equal to 1/2, and that's where we get this 1/2 here. Okay. Well, so pi u, actually, we got is bigger or equal to divide by 1/2 here. Pi u is bigger or equal to pi k plus pi over 12. Right, so it's pi k, over, right, sorry, it's pi, pi k plus pi over 12. So that should be a pi over 12 here. Not that it matters all that much, but anyway. Right. So that takes care of everything, the whole integrand. So this interval has length 1/6 for any x. That's the 1/6 here. This interval has length 1/12. So it's going to be 1/12. 1/12 is 1/24. Multiply this through, and we get 24 pi k plus 2 pi. So the L1 norm of S1F is bigger or equal to the sum here, and that's infinite. And like I said, it shouldn't be hard to imagine that modifying this a little bit, you can come up with a function f where this, basically a characteristic function where SR, FR, and L1 norm for any R is infinite. Okay. Okay, so how do we prove that? Sorry, this should be LP intersect L1. How do we prove that this is bounded? Well, this is not trivial at all. In particular, like with Fourier series, basically, we've just about proved that the Stirschle kernel here is not L1. Actually, basically doing what we did for Fourier series proves that this is not L1. Yeah, so because this is not an L1 function, it's not trivial at all. We don't have a trivial L. We don't have a trivial LP bound. In particular, by Young's convolution inequality, if dr was L1, we could get that, this here is less than or equal to the LP norm of G, L1 norm of dr. But it's not. Dr is not an L1. So yeah, this is not trivial at all. And actually, we basically left hanging the question of, for Fourier series, do we have LP bounds for F convolved with Dirichlet kernel on L1? And we will get back to that in a little bit. But yeah, and we're going to reduce matters just like we're doing here. For Fourier series, we're going to reduce matters for Fourier series to boundedness of a kind of Hilbert transform for the circle, which is very, very closely related to the Riesz projection, which is the same thing as a Hardy space projection on the circle, which if you're taking Professor Zhu's course, you probably discussed that. Okay, so for any dimension, let's look at some very useful operators. Particularly, let's look at multiplication by this complex exponential e to the 2 pi I a. So what I mean by this here is, as a function of x itself, this is just f of x e to 2 pi, oops, sorry, funky looking pi there, 2 pi I a, should be a dot here. So 2 pi a dot x, that's what this function is. So we want to take the Fourier transform and see what that is. And it has a very interesting property, very important property. So just plop this in, f of u e to 2 pi I a dot u. Sorry, again, there should be a dot here. That, we're integrating that against e to the minus 2 pi I x dot u. We'll just combine these two exponentials together. And this is a Fourier transform of x minus a. So in other words, we shift the Fourier transform, and it has the effect of inside the Fourier transform multiplying by this complex exponential. Similarly, if fa of u is just shifting by a, f of u plus a, let's take the Fourier transform. We'll just plop this in, do a change of variables. V is a plus u, so u is v minus a. Well, you could just distribute this. This is going to be equal to e to the minus 2 pi I x dot v. E to the minus 2, or rather, minuses cancel. So it's e to the 2 pi I x dot a. Well, lo and behold, there's no v here. This is just a constant. Pull this out. And this one just gives you the Fourier transform. So if we Fourier transform a shift, we get e to the 2 pi I x dot a. Now, not that we're going to do anything really super applied, but in engineering, this is extremely important because what is this saying? We're taking a signal and we're modifying the frequency. So we're kind of shifting, if we take a Fourier transform or shift, we are modifying the frequency by this complex exponential. So yeah, very important properties for in engineering. And if you pick up a digital signal processing book, and actually, I actually have one right here. If you're maybe not the best, but yeah. So in a little bookcase I have here, you can kind of see these kind of things in practice. This is actually not bad, Shaw's DSP. But anyway, yeah. So you can see Fourier transform and Fourier series in very concrete action in a very engineering perspective. But anyway, okay, so let's put this to good use. Let's define the Hilbert transform for an L2 function to be the following. So just take a function f, its Fourier transform is well defined if it's an L2. Multiply that Fourier transform by the sine function, SGN. That's just the usual. Oftentimes it's not defined at the origin, but you know, doesn't really matter, honestly. So this is the graph of this is a graph of SGN x. It's just 1 of x is positive, minus 1 of x is negative. All right, so let's multiply that and put in a minus 1 here. So one thing important to notice is that, well, let's figure out what the L2 norm of HF is. Well, by Fourier isometry, that's just going to be the L2 norm of minus I SGN x f hat of x 2. Well, this is 1 almost everywhere in modulus, except for 0. So this is Fourier transform of L2. All right, so lo and behold, this is a isometry. So it's an isometry on L2. All right. Okay, so in particular, it's certainly well defined, no issue, a fairly nice operator on L2. Okay, so let's say MA is multiplication in dimension 1 by this complex exponential, and as we just saw, we take the Fourier transform, it's just shifting by A. Okay, so, and I should mention that this is fairly trivially bounded on all LP for any P 0 to infinity, because you take modulus here, well, it's just trivially, as long as A is real, which it is here, this is going to be equal to the modulus of f of x. So, right. So this operator here is certainly an isometry on L2 because of this fact right here. We have just 3 isometries on L2. All right, so let's take A, apply it to F. Right, so let's take A, apply it to F. Right, and let's unravel things here. Okay, so, right, so take the Fourier transform here. It's going to be the Fourier transform of this whole thing here, plug in x plus 1. That's exactly this here. It's the Fourier transform of whatever m is applied to, x minus a. A is minus 1 here, so it's x plus 1. Okay, well, what's the Fourier transform of what's the Fourier transform of the Hilbert transform? Well, just by Fourier inversion, it gets rid of this inverse Fourier transform. So it's minus sine of x plus 1 times, well, the Fourier transform of whatever's inside here of x plus 1. Well, that is the Fourier transform of, well, take x plus 1 minus 1. So it's f hat of x. I's cancel, 1/2 sine x plus 1. And do the same thing for this operator here. We get the Fourier transform is minus 1/2 sine x minus 1 Fourier transform. So the conclusion here is that if we take a plus b, apply it to f, Fourier transform, well, we get this here, and you can check just point-wise that this is exactly going to be the characteristic function of this interval here. And that's just literally checking the 3 different cases. X is bigger or equal to 1, x is between minus 1 and 1, x is bigger or equal to 1. Okay? Now, if we take inverse Fourier transform, we get exactly that. S1 of f is given by this operator here, at least for f in L2. Okay, so let's put all the pieces we've been talking about together. So we just proved that for f in L2, and in particular f in L2 intersect LP, S1f is given by this operator here, which connects the Hilbert transform to S1. Now that's great, but we really want and need this for f in L1 intersect LP. So to rid ourselves of this annoyance, let's once and for all state the following, which I'll leave as a easy homework. Actually, it's not, I mean, it's not hard, but I'll give hints as to how to do this in the next homework. That this supremum that we're looking at, we want this to be bounded. If this supremum, remember, is bounded, then we will have LP convergence of Fourier transforms. We'll have a version of Fourier inversion for LP functions. Okay, well, this supremum here is given by the same supremum, but we're just taking Schwartz functions G. Okay, so in particular, Schwartz functions are in L1, they're in LP, they're in L2, they're in every LP for any P. So in particular, this holds for Schwartz functions. So putting this all together, we have our version of Fourier inversion for P between 1 and infinity. Well, if this is finite, which is true if this is finite, well, this quantity is certainly finite if the Hilbert transform, corresponding Hilbert transform bound from Schwartz functions to LP is finite. And that's just because, as we mentioned before, all these MAs, well, they're isometries on every single LP space because, well, this just equals absolute value of f of x, or modulus f of x if f is complex valued, at least for a real. So, right, so you trivially have MA LP to LP. These are all equal to 1. So certainly, right. So certainly, if f is a Schwartz function so that this holds, then certainly you can, you know, the LP norm of S1F is going to be less than or equal to, well, actually, it's going to be less than or equal to the LP norm of HF, simply because, or rather, sorry, maybe, yeah, so maybe I'll do it like this. So it's going to be, and if you have any doubts about this, there really shouldn't be, but you can check, just check using this fact here that every one of these has norm 1, that this is going to be less than or equal to this operator norm from the short space to LP. Right, where again, this is defined as the following norm. Okay, and what we'll do, I don't know if it's in the next video or if it's just very soon, but as long as we have a Schwartz function, we can have a very concrete realization of the Hilbert transform. And it turns out to be a very, very simple operator. It's actually the following operator. It's just simply the limit as epsilon goes to 0 integrate over y is bigger than epsilon, f of x minus y over y, remember in dimension 1, dy. So this is not trivial at all. We're going to prove this. And this is going to hold for a Schwartz function. So this reformulation in terms of Schwartz functions allows us to really get our hands on what this operator really is, or a concrete realization of this operator. Okay, so I just want to quickly talk about the situation in higher dimensions. Well, it's a very deep result and a surprising result by Charles Pfefferman, who is a Fields medalist. This paper is one of many papers that frankly won him the Fields Medal. That this is not true what I'm doing in higher dimensions. And I should mention that we will prove that this is true if P is 1, that this operator norm is bounded. Okay? So the result in higher dimensions is this operator norm is finite in higher dimensions precisely if and only if when P equals 2. Now, of course, I mean, this is trivial when P equals 2. The fact that this is bounded. So remember, what is actually S1? So, I mean, yeah, what is S1? Just to remind you. Well, it's a characteristic function, ball center 0, radius 1, times Fourier transform, inverse Fourier transform, well, Fourier isometry, this is characteristic ball. So actually nothing special about the characteristic ball. This is true for any characteristic function, really, when we're doing with L2. Thanks to the isometry property, this is less than or equal to the L2 norm of F. So actually, this operator norm is bounded by 1 on L2. And hence, I guess really it should be if and only if. Maybe it makes it a little clearer. But the really, really deep thing is that this is unbounded when P is not equal to 1 in higher dimensions. Yeah, and he actually gives an example when D equals 2, can reduce every dimension to D equals 2. And it's a really beautiful geometric construction on the just the two-dimensional plane, kind of cooking up a function f where things get screwed up. So yeah, very deep result. Anything in the annals of mathematics, you can be assured is pretty darn deep. But this is one of the most famous, deepest papers in all of harmonic analysis. And the really point you should get out of this is that the study of the Fourier transform in higher dimensions, kind of the LP study of Fourier transforms, Fourier inversion on higher dimensions is very, very difficult. There are some results, along the lines of what we're doing in the book Duo Andocotexia's Fourier analysis in chapter 8, but we probably won't be able to get to that. Okay, yeah, so as I said, the rest of the course is going to be basically devoted to proving this fact here for P between 1 and infinity. How do you prove this? That's going to be what the course is devoted to. And we have to develop some tools to do this. Okay. All right, well, so long. Take care. Until next time. And again, please do give me homework soon. Thanks. Bye-bye.